This is your presenter Asloop Mudassar, and I am presenting slide number 85 of the course on laser physics. Question is, assume that a resonator consists of two mirrors and that the propagation of a ray for the one round trip between the two mirrors is described by an ABCD matrix. Determine the condition of the resonator stability in terms of the matrix elements. Also express the stability condition in terms of the radii of curvature of the mirrors. Analyze that condition. The answer is, consider a simple resonator consisting of two mirrors separated by a distance capital L as shown in figure number 1. The mirror 1 has a radius of curvature R1 and the mirror 2 has a radius of curvature R2. Assume that a ray is incident on a point P. A ray is incident on a plane P just in front of the mirror 1 at point P0. This is shown in the figure that a ray is incident. You see that we have shown up a plane P just in front of the mirror 1. You know that in the formation of the ABCD matrices, especially when we are dealing with the curved surfaces of a lens or the curved surfaces of mirrors, we draw a plane just in front of the lens or just in front of the mirror. For example, just in front of the mirror number 1, we have drawn a plane P labeled with the P. And similarly, for the calculation purposes, we shall also draw a similar plane parallel to the plane P just in front of the mirror 2. And the calculations will be done from this plane. From the calculation, for the purposes of calculation, we shall choose a plane P, not the curved surface. So I have shown a point P not at which a ray is incidental, and then from the point P0 the light is reflected towards the mirror M2, and from the mirror M2 it is reflected towards the point P1. So from P0 to the mirror 2 and then back to the point P1, it will complete one round trip. And after one round trip, the light which is produced or the ray which is reflected from the point P1 is represented by the R1 vector. So similarly, the R1 vector will complete a round trip and will hit the plane P at another point which we call as point P2. And after point P2, we have the vector R2, which we have not shown. We have not shown point P2 and we have not shown the vector R2. But of course, we have shown point P0 and point P1. Similarly, when the second round trip will be completed, the point P2 will also be lying on the plane P, somewhere below the point P1. And from the point P2, the light will be reflected with a vector R2 represented by the R2 vector. The ray will be reflected represented by the R2 vector. And you know that when we are formulating an ABCD matrix, we talk about the rays, not the waves. So that's why I have shown the rays only over here. So we want to do the calculations, and you know that in this we have a statement that ABCD is the matrix for the one round trip between the two mirrors. So I am using this information that supposing that ABCD matrix from the point P0 towards the mirror M2 and then back to the point P1, for that one round trip the matrix is described, this ray tracing is described by the matrix ABCD as stated in the question. The ray reflected from P0 has the transverse coordinates R0 and angle θ0 with respect to the horizontal axis or the optic axis. The horizontal axis is shown as the line joining point 1 and 2 on the mirror 1 and mirror 2, or this may also be taken as the optic axis, because it joins the mirror 1 and the mirror 2 at the points where it is normal to both the mirrors. So this is referred to as the optical axis or the horizontal axis. And at the point P0, we have R0, we have two values of vector R0. One is the magnitude, which is R0, the other one is the angle θ0, which the ray is making with the horizontal axis. And similarly at point P1, the light will make an angle. The light has a transverse coordinate r1 and the theta and the angle theta1 with the horizontal axis. And similarly at the point P2, which we have not shown, the magnitude of the transverse angle of the transverse magnitude of the transverse coordinate will be r2, and that will make an angle theta2 with the horizontal axis. And you know that point P2 has not been shown. If the point P2 is shown, then of course the light reflected from the point P2 will be represented by the vector R2, and that will make an angle theta2 with the horizontal axis. So this is what I have stated in this paragraph, that the ray reflected from P0 has the transverse coordinate R0 and the angle theta0 with respect to the horizontal axis or the optic axis. The ray after reflection from the mirror 2 is incident on mirror 1 at point P1 and is reflected as ray 1, represented by the vector R1, which has a transverse coordinate R1 and the angle theta1 with respect to the optic axis. The parameter of R1 can be expressed in terms of the parameters of R0 using the matrix transformation, that is for one round trip, because the one round trip will complete when the light will leave the point P0 and will be reflected from point P1. So this will form one round trip. And after one round trip, the coordinates of the ray was represented by the vector R1, and the initial coordinates of the ray which leaves the point P0 is represented by the vector R0. So we can connect the vector R1 with the vector R0 with the ABCD matrix, because we are assuming that the ABCD matrix of the system is known. So here we have written down that the parameters of R1 can be expressed in terms of the parameters of R0 using the matrix transformation as given. So we have a column vector of R1 and theta1 on the left hand side, which is equal to the product of ABCD matrix, which is the system matrix for a general optical system such as shown in figure number 1, and then multiplied by the column vector R0 and theta0. So this is the calculation after one round trip. So after the second round trip, the ray 2 will be reflected from the point P2 on the plane P. And you know that I have mentioned that point P2 and the ray R2 has not been shown. But of course, these will appear when the second round trip will be completed. The matrix transformation between the parameters R2 vector and the parameters R1 vector will take the following form. So you have, now you can connect the vector R2, the parameters related with the R2 ray and the parameters related with the R1 ray can be connected similarly through the ABCD matrix. That is R2 theta 2 as a column vector on the left hand side is equal to the ABCD matrix on the right hand side multiplied by the column vector R1 and theta 1. You know that R1 and theta1 column is given by equation number 1. So we can substitute the value of R1 and theta1 in the next step over here, and then we have the matrix which is the square of ABCD matrix, then multiplied by the initial value of the ray R0 and theta0. So this is after the second round trip. Thus, after the nth round trip, we have the following relationship. Rn theta n, the ray after the completion of the nth round trip, the coordinates of the ray are Rn and theta n, and we have written them as the column vector on the left hand side, which is equal to the nth power of the ABCD matrix, because we have now completed the n round trips in that system, and then multiplied by the initial value in the form of a column vector which is R0 and theta0. So this is the result that provides us to calculate the ray parameters after completion of n round trips. The resonator will be stable if the point after nth round trips does not diverge. That is, Rn and theta n do not diverge. If we assume that the two surfaces of the resonator exist in the same medium, that is both have the same, that is that there is the same refracting index for the two medium, for the two surfaces, then the determinant of the ABCD matrix will be equal to unity. This is by definition of the ABCD matrix. Notice that we have also discussed the properties of the ABCD matrix in one of our previous slides on the course on the laser physics. You can also consult that slide if you want to know the property, and here I am mentioning only particular property that if the two optical elements are contained in the same medium, then the determinant of the ABCD matrix will be equal to unity. A theorem of the calculus states that if cos of theta is equal to a plus d divided by 2 as given in equation number 3, then we can write the nth power of the ABCD matrix equal to 1 over sine of theta, and then we have a square matrix of 2 by 2 containing the elements in the first row are a sine of n theta minus sine of n minus 1 into theta, and then the second element of the first row is capital B times sine of n theta. And in the second row, the first element is c into sine of n theta, and the second element of the second row is capital T multiplied by sine of n theta minus sine of n minus 1 into theta. So you see that now we have formulated a simplified version of the nth power of the ABCD matrix in the form of the matrix shown on the right hand side of equation number 4. It can be established that the nth power matrix does not diverge. It can be established that the nth power matrix does not diverge if theta is a real quantity. For example, if you solve the equation number 3 and you get the real value of theta, then it means that the matrix ABCD raised to power n will not diverge. Since cos of theta lies between -1 and +1, thus we can write that a plus d divided by 2 is greater than has a value lies between -1 and +1. That is a plus d divided by 2 is greater than -1 and less than equal to +1. Or a plus d divided by 2 is greater than equal to -1 and less than equal to +1. So this is that is equation number 5 gives you the condition which we call as the stability condition. This is the stability condition of a general optical resonator having ABCD as matrix of the resonator. The ABCD matrix of the optical resonator shown in figure 85.1 is obtained as given. Now you see that we have this optical system which I have shown over here, and now we are going to formulate the ABCD matrix for this system. First of all, the light will travel from P0 to the mirror M to the mirror 2. So it will travel a free space propagation from P0 to a point on the mirror 2. So it will travel a distance capital L in free space. And here we are assuming a refractive index equal to air. So the first element is written on the rightmost side of the matrix, that is 1, capital L, 0 and 1. So this represents a free space propagation from the point P0 to a point on the mirror M2. Then you know that the reflection will take place at the surface of the mirror M2, and that reflection is represented by the second matrix from the right hand side, that is 1, 0, minus 2 over R2 and then 1. Then the light will travel after reflection from the mirror 2, it will travel towards the point P1. So it means that it will travel a free space propagation equal having a geometrical length equal to L. So we are going to insert that matrix at the third position, that is 1, L, 0 and 1. And then you see that the reflection will take place at the point P1. So the refraction matrix at the point P1 is 1, 0, minus 2 over R1 and 1. So you see that for one round trip, I have written an ABCD matrix for the one round trip in the optical system shown in figure number 1. And the matrix is ABCD matrix. So if you multiply all these together matrices, you will get an ABCD matrix. And I am going to discuss the A and D variables, the value of A and D parameters of the matrix only, because you know that the stability of the optical resonator is given by this condition, which involves A and D, two elements of the ABCD matrix. So I am going to discuss only these two. So A plus D divided by 2 is equal to 1 minus 2L over capital R1 minus 2L over capital R2 plus 2L square over R1 into R2. So if you do the multiplication of these four matrices, you will get the value of A, B, C, and D by equating the left hand side with the right hand side, and then adding the value of A and D and dividing it by 2, you will get the value on the right hand side, which is 1 minus 2L over R1 minus 2L over R2 plus 2L square over R1 and R2. So you see that I have written this one in the following form, that is equal to 2 times the square bracket containing 1 minus L over R1 and another square bracket containing 1 minus L over R2, and then minus 1 is subtracted from the product. So this is A plus D divided by 2. Now for further simplification, I am assigning some variables to this one. So let's define G1 and G2 as the parameters of a resonator, as G1 is equal to 1 minus L over R1, and we are defining G2 is equal to 1 minus L over R2. So in terms of the values of G1 and G2, we can say that A plus capital D divided by 2 is equal to 2 times of G1 into G2 minus 1. Because in the square bracket we have G1 and G2. So 2 times G1 and G2 minus 1. This is what we have written. Or simply you can say, you can insert this value, that is 2G1, G2 minus 1 over here. So A plus D divided by 2 can be replaced by its value, which is 2 times of G1 and G2, thus greater than minus 1 and less than plus 1. So you can adding plus 1 throughout this one. So adding plus 1 throughout all the terms, we have 0 is less than 2G1, G2 is less than 2. And then dividing all the terms by 2, you get 0 less than G1, G2 less than 1. So finally we have reached this simplified condition, and this inequality has been labeled as equation number 7. This is another form of the stability condition of the resonator. So you see that this condition is also the condition of the resonator. And you know that this G1 and G2 is in terms of the radii of curvature. And in the question, we were asked to establish the condition of stability of the resonator in terms of the radii of curvature. And this is what we have done in equation number 6. And we have stated the same equation number 6 in the following form as shown in equation number 7. That is, the product of G1 and G2 is greater than 0 and less than 1. This is another form of the stability condition of the resonator. Let us plot the stability condition with G1 along the horizontal axis and G2 plotted along the vertical axis. The plot is shown in figure number 2. So you see that you can see that I have plotted G1 as a variable on the horizontal axis and G2 as a variable on the vertical axis. Of course, the G1 and G2 are greater than 0 in the first quadrant. And of course, G1 and G2 are both less than 0 in the third quadrant. Now you see that we have to establish this condition, that is the product of G1 and G2 is equal to 1. We have written, because this product of G1 and G2 is equal to 1 represents this solid line, which is a curved line in the first quadrant. And similarly, G1, G2 is equal to 1 also represents a solid line passing through the point A in the third quadrant. This solid line is also represented by G1 to G2 is equal to 1. And you know that here G1 and G2 is equal to 1 in the first quadrant also passes through the point C. And you know that we have joined A and B. We have joined A and C, and of course there is also a point B at the vertex, at the coordinate axis, at the center of the coordinate axis. So the origin of the coordinate axis of the G1 and G2 is represented by capital B. This is what we are going to explain, that why we have labeled A, B and C at specific positions. The caption of the figure is plot of the stability region of the resonator indicated by the dots. These are the dots, the solid black dots. These represent the stability of the resonator. If you choose the value of R1 and R2 in such a way that you get in the plot, you get a point either in the horizontal curve or in the vertical curve, that is the solid point, then of course your resonator will be stable. And if you get any point on these solid curves represented by G1, G2 is equal to 1, both passing through the point C in the first quadrant or the point A in the third quadrant, then you see that the stability will be declared as marginal. But if the points correspond to the solid points represented by black dots, then of course the stability, then the system, then the resonator will be stable. The dotted region is the region where the resonator is stable. Along the line A to C, the resonator has identical mirrors, that is R1 is equal to R2 is equal to R. So you see that this is the reason that why we have joined A to C. Because if you join A to C, then of course the value of G1 and G2 will be the same for point A. Of course, both will have the 0 for the point B and both will be positive, but it will be equal to each other for the point C. So the R1 is equal to R2 is equal to R for the point A, for the point B, for the point C. Though the values will be different of R1 and R2 will have different values for point A, for point B, for point C, but for any of these points, the values of R1 and R2 will be equal to each other and will be equal to, say, capital R. Now we are going to do some calculations for the point A. The point A corresponds to the concentric resonator. Because for such a resonator, we have capital L is equal to 2R. So if you put the value of capital L is equal to 2R over here, because we have defined G1 is equal to 1 minus L over 2R, and if you put the value of L is equal to 2R, and similarly in the second G2 is equal to 1 minus L over 2R, and again if you put the value of L equal to 2R, and you see that R1 also equal to R and R2 is also equal to capital R, because as mentioned that from that for the points A to C, A, B, C, we have the same radii of curvature for the individual points. So if you put the value of L is equal to 2R in the above equations, you will get G1 is equal to -1, G2 is equal to -1. You see that G1 and G2 both have the same values and both have values equal to -1. That's why we have a point A over here. And this point is only possible when we have the distance L is equal to 2R. And L is equal to 2R means that we are talking about the concentric resonator. The concentric resonator has also been discussed in the previous slide, that is in the slide number 84. Because you see that G1 was defined as 1 minus L over R, G2 is equal to 1 minus L over R, and if you put the value of L is equal to 2R over here and over here, you will get G1 is equal to -1, G2 is equal to -1. But the product of G1 and G2 will be equal to +1. So the curve G1 and G2 is equal to +1 in the third quadrant will pass through the point A. Because G1 and G2 satisfies the condition of G1, G2 is equal to 1. Now let's discuss the point B. The point B is located over here at the origin of the coordinate system formed by the G1 and G2 as the axis of coordinate system. So let's talk about B. You see that B has 0, 0 coordinates. That is, the value of G1 is 0 at point B, and the value of G2 is also 0 at point B. So under what condition we get G1 is equal to 0, G2 is equal to 0? Let's see that one. The point B corresponds to the confocal resonator, because L is equal to capital R for such a resonator, which gives G1 is equal to 0, G2 is equal to 0. So you see that if you put capital L is equal to capital R, G1 becomes 0. Here again, if you put capital L is equal to capital R, G2 becomes 0. So G1 and G2 both gets value equal to 0. So we have G1 is equal to 0, G2 is equal to 0. The product of G1 and G2 is also equal to 0. Thus, the point B corresponds to the origin of coordinate system over here, because both G1 and G2 have 0 values, and then point B is required to have a resonator which is the confocal resonator, because for that one L is equal to R, and only L is equal to R will ensure the two values to be equal to 0. Now let's talk about the point C. The point C corresponds to the planar resonator. You know that in the planar resonator, both the R1 and R2 will be infinite in diameters, will be infinite in the radii of a curvature. So if you put infinity over R, if you set R goes to infinity in the value of over here, you will get G1 is equal to 1. And if you put R goes to infinity, L over infinity becomes 0, and then you will get G2 is equal to 1. So for the third case, that is for the case of point C, we are getting G1 is equal to 1, G2 is equal to 1, and the product is also equal to 1. So G1 and G2 both have the same values for the point C. So point C, G1 and G2 both are equal and has a value equal to 1 each. And the product has also value equal to G1 equal to G2 is equal to 1. So the curve of G1 and G2 equal to 1 will pass through the point C, because the point C has a coordinate G1 is equal to 1, G2 is equal to 1, that satisfies the curve given by G1 and G2 is equal to 1. Okay, so we have also explained the point C. So the point C represents the planar resonator, point B represents the confocal resonator, and point A represents the concentric resonator. On the horizontal axis, we have G2 is equal to 0, and on the vertical axis, we have G1 is equal to 0. Obvious, that is obvious. That is on the horizontal axis, which is represented by G1, the value of G2 is 0, and on the vertical axis represented by G2, the value of G1 is 0. Okay, that is on the G1 axis and G2 axis, we have G1 multiplied by G2 is equal to 0. So on both axes, we have G1 is equal to G2 is equal to 0, because one of them is equal to 0 and the other will be non-zero, but the product will be equal to 0. The dotted area bounded by G1, G2 is equal to 0 and by G1, G2 is equal to 1 is the region where the resonator is stable, whereas the points on G1 and G2 is equal to 0, or the points on G1 multiplied by G2 is equal to 1 indicate marginally stable resonators. So if you put the values if you choose a radii of curvature R1 and R2 in such a way that your data lies on the G1 curve, on the G1 line or on the G2 line, then your resonator will have the marginal stability. Or if you have a radii of curvature chosen for your resonator in such a way that you get G1, G2 is equal to 1, either for the first coordinate quadrant or for the third quadrant, then for the points lying on the G1 and G2 is equal to 1 curve, the resonator will have marginal stability. But you see that you see that in between the two curves, that is the curve represented by G1 G2 is equal to 0 and G1 G2 is equal to 1, indicated by the dotted lines, solid dotted lines. These are the points at which your resonator will be stable, and this is what I have stated over here. the dotted area bounded by G1, G2 is equal to 0 and G1, G2 is equal to 1. The area bounded by these two is the region where the resonator is stable, whereas the points on G1 and G2 is equal to 0 or the points on G1, G2 is equal to 1 indicate marginally stable resonators. So you see that we have answered all the questions, all the queries of the questions in our answer, and we have covered all aspects raised in the question. So this is the end of slide number 85.